So in my video on the introduction to hydrostatics, we talked about how on the Earth, let's say this is the Earth, the atmospheric pressure is greatest near the surface of the Earth, whereas if you're on the top of Mount Everest, let's say, the atmospheric pressure will be less. And we also learned that this is for the same reason that if you're deeper in a body of water, let's say, the pressure as you go deeper in the water will be greater than the pressure further above. So the deeper you go in water, the pressure gets greater. And we also learned that if you want to find the pressure at point 2, all you have to do is take the pressure at point 1 and add the density times the gravity times the depth, or the height difference in between the 2 points. So there's one more important thing that you need to know about hydrostatics, and that is called the first law of manometry. So the first law of manometry says that a horizontal surface is an equal pressure surface if there is a continuous connection of fluid, and the fluid is a constant density. So if, let's say we have this really weird looking container of water right here. Since this fluid has a constant density, this water inside the tube, the pressure at point A is actually going to equal the pressure at point B because they both have the same height. So if we have two different liquids in this weird shaped tank, that means that the pressure at A is not going to equal the pressure at B. And since these liquids have different densities, they're going to exert different pressures at point A and point B. So if you remember our initial equation, pressure equals the density times the gravity times the depth. The greater the density, the greater the pressure. So that means that the heavier the liquid is, the more pressure it's going to exert at a certain point. So let's say we wanted to find the pressure at point 5. So what we're going to do is we're going to start out at point 1. And we are going to move along the tube until we get to point 5, and then we'll find the pressure doing that. Just like we did in the last example, where if we wanted to find the pressure at an area below a certain point in a liquid, we would just take the pressure above and add the rho GH of that point below. So I'll show you what I mean. So we want to start out with the pressure at point 1. And if we want to find the pressure at point 2, what we have to do is take the pressure at point 1 and add rho, which is the density of water, times gravity, times the height difference. So the height difference between these two is going to be 250 millimeters, as you can see right here, or in other words, 0.25 meters. So the next thing we want to do to find the pressure at point 3 is we want to subtract the density of the oil times gravity times the height difference between point 2 and point 3. Now this is going to be 250 millimeters plus 25 millimeters, which is 275 millimeters or 0.275 meters. And another reason why this works is because the pressure at point 2 and the pressure right here is going to be the same, since we have the same liquid and they're on the same horizontal surface. So again, at point 4 is higher than point 3, so the pressure is going to be less. So therefore we have to subtract the pressure because we have a positive height difference. All we have to do is subtract the density of air, since this is the medium which we're dealing with, times gravity times the height difference, which is 150 millimeters or 0.15 meters. And then going from point 4 to point 5, the pressure will increase since there is a negative height difference. And we're dealing with the oil again, so all we have to do is add the density of the oil times the gravity times the height difference, which is 0.15 meters. And all of this is equal to the pressure at point 5. Now, this question didn't give us any specific values for the pressure at point 1, but if we had the pressure at point 1, we would be able to get the pressure at point 5 using this equation that we just made. In this example, we're given a closed tank with a little outlet right here where the liquid is rising up due to the pressure of the tank. So the gauge pressure inside the tank is measured to be 4.5 times 10 to the 4 pascals, and the liquid inside the tank has a specific gravity of 0.8. So what we're trying to find is the pressure at the bottom of the tank at point 1, and we're also trying to find out this height. We're trying to find out how high the water is going to rise up this tube due to the pressure in the tank. So the first thing that we can tell is that the pressure at the top of the liquid right here is the same as the gauge pressure. So let's call this point 2, since the bottom is already called point 1. So if we wanted to find the pressure at point 1, we would just do what we've been doing in the last couple examples, where we take the pressure at the top of the liquid and just add the density times the gravity times the depth of the liquid. So writing that out, we can say that the pressure at point 1 equals the pressure at point 2 plus the density of the liquid times the gravity times 1.5 meters, which is the depth of the liquid. So another way we can write this is P1 equals P2 plus S, which is a specific gravity, times the density of water times gravity times 1.5 meters. So this kind of speeds things up because then we don't have to find the density of the liquid. We can just multiply the specific gravity times the density of water, which speeds things up. So if we take these numbers and put it in on our calculator, we will get 56,772 pascals. So that is the pressure at the bottom of the tank. So now we just need to find out how high the water has traveled up the tube due to the pressure in the closed tank. So to start out this question, we found the pressure at the bottom of the tank based on the depth of the liquid from the top of the closed tank. So how we're going to solve this question is we're going to find the pressure at the bottom of the tank using the height of this water. Since we already know the pressure at the bottom of the tank, we can just write an equation for finding the pressure at the bottom of the tank based on this distance right here, and then we can just solve for the desired height. So the equation that we're going to write is the pressure at the bottom of the tank at point 1 equals the specific gravity of the liquid times the density of water times gravity times the height. And we'll call this height capital H. Now capital H equals the height of the water plus 0.5. And this is because the distance between the bottom of this tube and the bottom of the tank is 0.5. If we just do 1.5 minus 1. So now we can just substitute the H into the equation and we get P1 equals the specific gravity times the density of water times gravity times H plus 0.5. And we already know that the pressure at the bottom of the tank is 56,772. So we can substitute that into the equation. Now, if we just plug this in on our calculator, we'll find that H equals 6.73 meters. So that means that due to the pressure of the closed tank, the water rises up this tube by 6.73 meters. So this works because the gauge pressure at the top of the tube is actually 0. So we're just using this point at the top as a reference point and finding the pressure at the bottom of the tank using this distance as the height, which we called capital H.